Plant-derived materials such as cellulose often exhibit thermally insulating properties. A new material made from nanoscale cellulose fibers shows the reverse, high thermal conductivity. This makes it useful in areas previously dominated by synthetic polymer materials. Materials based on cellulose have environmental benefits over polymers, so research on this could lead to greener technological applications where thermal conductivity is needed. Cellulose is a key structural component of plant cell walls and is the reason why trees can grow to such heights. But the secret of its material strength actually lies in its overlapping nanoscopic fibers. In recent years, many commercial products have used cellulose nanofiber, CNF, materials because their strength and durability make them a good replacement for polymer-based materials such as plastics that can be detrimental to the environment. But now and for the first time, a research team led by Professor Junichiro Shiomi from the University of Tokyo's Graduate School of Engineering has investigated previously unknown thermal properties of CNF, and their findings show these materials could be even more useful still. If you see plant-derived materials such as cellulose or woody biomass used in applications, it's typically mechanical or thermally insulating properties that are being employed, said Shiomi. When we explored the thermal properties of a yarn made from CNF, however, we found that they show a different kind of thermal behavior, thermal conduction, and it's very significant, around 100 times higher than that of typical woody biomass or cellulose paper. The reason yarn made from CNF can see. Cellulose fibers in nature are very disorganized, but a process called the flow-focusing method combines cellulose fibers, orientating them in the same way, to create CNF. It's this tightly bound and aligned bundle of rod-shaped fibers that allows heat to transfer along the bundle, whereas in a more chaotic structure it would dissipate heat more readily. Our main challenge was how to measure the thermal conductivity of such small physical samples and with great accuracy, said Shiomi. For this, we turned to a technique called T-type thermal conductivity measurement. It allowed us to measure the thermal conductivity of the rod-shaped CNF yarn samples, which are only micrometers, a micrometer equaling 1/1000th of a millimeter, in diameter. But the next step for us is to perform accurate thermal tests on two-dimensional textile-like samples. Shiomi and his team hope that their investigation and future explorations into the use of CNF as a thermally conductive material could give engineers an alternative to some environmentally damaging. In applications where heat transfer is important, such as certain electronic or computational components, it could greatly reduce the consequences of discarded electronic equipment, or e-waste, thanks to the biodegradable nature of CNF and other plant-based materials. Make a difference. Sponsored opportunity story source. Materials provided by University of Tokyo. Note: content may be edited for style and length. Journal reference: Guantong Wang, Masaki Kudo, Kazuho Daicho, Sivasankaran Harish, Bin Shu, Chang Xiao, Yaerim Li, Yuxuan Liao, Naoto Matsushima, Takashi Kodama, Frederick Lundell, L. Daniel Soderberg, Sugiyuki Saito, Junichiro Shiomi. Enhanced high thermal conductivity cellulose filaments via hydrodynamic focusing. Nanoletters, 2022, doi 10.1021, AX. Nanolet. 2CO2057. Cite this page, University of Tokyo. Plant fibers for sustainable devices. Research into thermal properties of cellulose nanofibers yields surprising results. Science Daily, the 4th of November 2022. ift.tt/qftxeo1. University of Tokyo, 2022, November 4. Plant fibers for sustainable devices. Research into thermal properties of cellulose nanofibers yields surprising results. Science Daily. Retrieved November 4, 2022 from ift.tt/qftxeo1 University of Tokyo. Plant fibers for sustainable devices. Research into thermal properties of cellulose nanofibers yields surprising results. Science Daily. https://ift.tt/qftxea1 accessed November 4, 2022. Thanks for watching. Please subscribe my channel for more videos.